We will now talk about some different ways that we can represent our coordinates when we're writing our input files. So we've talked about potential energy surfaces before, and we've talked about the fact that this is a way to represent the energy of a collection of atoms, basically our molecule, with all possible different nuclear arrangements. So however we want to set up our nuclei, whatever the energy is, that gives us this potential energy surface. And so we could define each structure by a set of x, y, and z coordinates for each atom, so using Cartesian coordinates. Since we have a total of n atoms, we'd have 3 coordinates for the first atom, 3 coordinates for the second atom, 3 coordinates all the way up to the nth atom. So it gives us 3n total coordinates. Now that's our total number of nuclear coordinates we could have. But, there are certain things that don't really change your structure. So if you were to translate your structure by moving it in the x direction, 1 angstrom, all we're doing is changing where that molecule is, but we're not really changing the orientation of the atoms with respect to one another. So we can remove the 3 degrees of freedom that correspond to the translations. And similarly, the structure doesn't really change if it's rotated. It's still the same structure as far as those atoms' relationship to one another. So we can remove 3 degrees of freedom for a 3-dimensional molecule or 2 degrees of freedom for a linear molecule. So in the end, the potential energy surface has 3n minus 6 dimensions, or 3n minus 5 for linear molecules. Again, this can be kind of hard to visualize, so we often take slices involving only 1 or 2 of the coordinates. Now, with the Cartesian coordinates, if you express your molecule in terms of Cartesian coordinates, you deal with those 3n total coordinates. You'll often have to think about how do you remove the translations and rotations. Another way of representing our structure could be in internal coordinates. So internal coordinates can sometimes be called z-matrix coordinates. And what the idea here is that we're going to use things like bond lengths, angles, and torsional angles to define the geometry. So the way we'll do this is if we had one atom, we really don't need to define the structure. We already know the structure, so there aren't any variables that are required. Now, if we start to have a system with 2 atoms, the only geometrical variable that we have is the distance between atoms 1 and 2, this R12 value. So we have one variable that's needed to define our molecule. That really corresponds to 3n minus 5. 3 times 2 minus 5 is 1, and that's because it is a linear molecule. Now, as we move to a little bit more higher number of atoms, if we have 3 atoms, for example, there are several ways we could do this. So I've got 2 ways shown here. One is we could define the distance R12, could define the distance R23, and then we could have an angle between atoms 1, 2, or 3. Alternatively, we could just define the 3 distances. Having 3 distances defined will actually define all of our angles as well. So we need 3 variables in this case. That actually corresponds to 3n minus 6 is equal to 3. Now if we move up to 4, now we have some options. So with 3 atoms, we always have to be in a plane. Now that we have a 4th atom, we may not be in that plane. It could be a bit out of plane. It could be planar. How do we determine, or how do we at least distinguish and denote this? Well, we'll have some of the same types of geometrical variables we had before. We'll have this distance R12, we'll have a distance R23, we can have distance R34, we can have angle between 1, 2, 3, an angle between 2, 3, and 4. And then we can have another angle, that is the torsional angle, that says how far out of the plane of 1, 2, and 3 is atom 4. Now, you wouldn't have to use those particular variables. You could use a different angle, for example, like the 1, 2, 4 angle will also give you another angle. So there could be several things you could use, but regardless of how you do this, you're going to end up needing 6 variables, which works out to be 3n minus 6. So 6 variables to define your geometry. So a typical Z-matrix could look something like this. We have our atom 1 first. When we have our atom 2, we are thinking about how is atom 2 in relationship to atom 1. Well, there's a distance R21. We could then define our third atom. We could choose a second atom and put a distance R32 between atoms 3 and 2. We can then have our third atom, atom 1, over here. Then we'll have an angle between 3, 2, and 1 that gets defined over here. Now for the atoms 4, 5, and 6, anything higher than that starts out the same. Atom 4 and atom 3, doesn't have to be atom 3, it could be atom 1 or atom 2. In this case, atom 4 and atom 3 has a distance R43. There's then an angle between 4, 3, and 2 that's represented here by angle 432. And then, this is the part that's different, we have a torsional angle between 4, 3, 2, and 1 drawn here. And again, even though I have these ordered numerically, it could be the torsional angle for 1, 2, 3 if we just put atom 1 here and atom 3 there. All right, now when we figure out for our sizes of the system, we still end up getting 3n-6 degrees of freedom, just because we don't have any geometrical variables defined for atom 1, we don't have an angle or a torsional angle for atom 2, or a torsional angle for atom 3. But so we end up with our 3n-6, and this might seem like a very logical way as well to define your coordinates, because it has some very physically related geometrical parameters. So now let's talk about two different water input files. These are GAMES input files for water. We can do them in terms of unique Cartesian coordinates or in terms of Z-matrix coordinates. So with our water file, we've got some of the dollar groups that we often see. We've got our control group specifying we're doing a Hartree-Fock optimization. Got some time limit and word memory parameters. In this particular case, we're setting up an STO3G calculation. Got a little bit tighter tolerance than the default. We'll do just 20 steps. And then here's our data. And our data is what's going to differ a lot between the two different input files. So in the first case, we are going to go ahead and actually use symmetry. So I'm writing in the fact this is a C2V point group. Because the two hydrogen atoms are related, either by the C2 axis or the mirror plane, they're equivalent. We only need to specify one. In this case, we can put an oxygen atom in, we can put one of our hydrogen atoms in, and we get our full water molecule that way. Now with Z-matrix coordinates, we have to actually define the fact that we're going to be using Z-matrix coordinates. By default, we use Cartesians. So here we've got our Z-matrix coordinates. Otherwise, things are pretty much the same until we get to dollar data. Again, we're defining the fact we have a C2V symmetry. In this case, we're using a Z-matrix. We've got atom 1 is oxygen, atom 2 is hydrogen. Hydrogen is connected to atom 1 with a distance of ROH. Atom 3 is connected to atom 1 with a distance of ROH. And there's a 3, 1, 2 angle, which is our angle HOH. And then at the bottom, we've got the ROH defined and the angle HOH defined. Again, this is a starting geometry. It was meant to be reasonably close to the experimental geometry, but of course, when we run the optimization, it'll be determining the best parameters at this particular level of theory, Hartree-Fock with an STO3G basis set.